In this video, we'll be talking about classification, another task of supervised learning. We know that we have some labeled data, as you can see on the left. These are the shapes, circles, squares, triangles, and hexagons. And we have some corresponding labels. We feed this data into a machine learning model and hope that it tunes its parameters and learns those patterns by itself. And then we provide it with some test data. And we hope that its output, the predictions, are the correct labels. This is once again a supervised learning problem. And unlike the previous regression problem where we had a continuous output, we can see that in this particular data set, we only have a discrete number of labels. This is what we refer to as a classification task. And one of the models, one of the most basic models to work with classification is the k nearest neighbor. The k nearest neighbors or KNN algorithm is a very basic and intuitive model. Uh, it's a supervised learning algorithm, once again, that classifies a point based on the majority of its k nearest neighbors. Essentially, what it does is that it searches in the surroundings and finds the closest points to it and assigns the label to the new point corresponding to the majority class. The algorithm is written on the left. We specify k, which is the number of neighbors you want to check. We compute distances from this new point to all of the points in our data set. We sort them and select the k nearest neighbors, meaning the k neighbors with the least distance. And among those, we assign the majority class. On the right, we can see a visual where we're changing the k parameter, and accordingly we can see that the labels are changing as well. With k equals 3, the label is blue because majority classes are blue. With k equals 5, once again the majority classes are blue. However, when k equals 7, the majority classes are now red and the label is red. As the model's name suggests, there is a significance of selecting the k value in k nearest neighbors. It directly affects how the algorithm classifies new data points, impacting the model's performance. The right k value balances capturing patterns and avoiding noise. A small k value can lead to overfitting, making the model overly sensitive to individual data points, while a large k value might cause underfitting, missing essential patterns in the data. You have to choose the value of k optimally using some iterative method to test different values of k on your data. I've also given a pseudocode for the Python implementation. You can see that on the screen now. And you can try implementing this yourself. It doesn't give the exact functions and the exact code, but a general guideline on how you'd implement it. I'll give a quick run through. Initially, you want to init the function by specifying k, and then you fit the data, which is essentially just copying the data into the class itself and nothing else. Then in predict, what you do is for each input sample of the testing data, you compute the distances with each of the training samples using some distance metric. And then you sort those distance metrics in ascending order, and you find the first k indices. And according to those indices, you assign a majority label. And down there, you can see that the distance metric we're using right now is Euclidean distance. Let's talk more about these distance metrics next. So the distance metrics are essential in k-nearest neighbors for assessing similarity between the data points. We'll delve into some common distance metrics used in KNN and their applications. First up is the Manhattan distance, also known as the city block distance, which sums the absolute differences between the coordinates. It's ideal for high-dimensional data space and discrete data. Then there's Euclidean distance, which is the go-to metrics for KNN classifiers. It computes the straight line distance between 2 points in multiple dimensions. This method excels in continuous data and is favored for its simplicity. There are other distance metrics such as the cosine similarity, which measures the angle between vectors. This is useful for textual analysis. Choosing the appropriate distance metrics is vital for KNN's performance, and it's something that you should optimize for your particular use case. The k-nearest neighbors algorithm is celebrated for its simplicity and clarity. It provides a very simple and direct method for classification, avoiding intricate mathematical derivations. And the ease makes it a prime selection for smaller datasets and fewer predictions. Let's examine the primary advantages and limitations of KNN. So the advantages include that it's quite simple to implement. There's no training phase, and it's adaptable for new data and effective on small datasets. There's also no assumption of the underlying data distribution. However, it has high memory requirements because you need the entire dataset to compute the distance between a new point and the training examples. With increase in training examples, once again, the computational expense increases exponentially, and it's sensitive to irrelevant features and requires feature scaling and struggles with imbalanced classes. Grasping these benefits and drawbacks aids in determining whether to employ KNN in machine learning endeavors. While it shines in simplicity and flexibility, it's essential to consider dataset size and dimensionality for the best results. Now that we've talked about the implementation, advantages, and disadvantages of KNN, let's look into some real-world applications. KNN is a widely used algorithm across various industries, and it's known for its ability to solve real-world problems effectively. It's used in finance for stock market prediction. It analyzes historical data to identify patterns and aids investors in making informed decisions. It's also used in credit scoring, fraud detection, and improving risk management. KNN is used in healthcare for medical diagnosis due to its pattern recognition capabilities. For example, KNN aids in predicting breast cancer symptoms by considering factors like mitosis levels. It's also used in recommendation systems, where KNN is used to suggest products, movies, articles to users by identifying similarities between user preferences, item features, and this can improve the overall user experience across platforms. Finally, KNN is also used in imaging processing for recognition tasks and segmentation tasks. It's a valuable tool in applications such as facial recognition and object detection. And that's it about KNNs. I hope this video equipped you with some foundational knowledge about the algorithm, as well as the ability to implement it on your own. If you've come this far and enjoyed the content, I hope that you'd consider liking the video so it reaches more people, as well as subscribing so that you don't miss out on new content.